Hi everybody. This is Bahman. I'm a senior lecturer in Cardiff University at Cardiff Business School. In this session, I'm going to present chapter 4 of the book, which is about curve fitting and exponential smoothing. So this book has 6 subsections, basically. So first of all, it explains a little bit about the chapter itself. Following that, we have a section dedicated to curve fitting. And then in subsection 3, we discuss the exponential smoothing methods. Following that, there is a very short subsection that talks about forecasting for intermittent demand series, and then following that we have a wrap-up and summary of key terms in the book. Well, if you use any software, it doesn't matter if it's open source software like R or a commercial software. There are many in the market, they do forecasting. At some point, you have to produce the forecast, but then you don't really need to deal with the math and formula and do it, for example, manually to be able to generate the forecast. The software will do it for us. However, I think it is important to understand the principles behind the forecast, especially in practice, and how these forecasts are generated and what are the rationales behind the math that generates the forecast. This is important in practice because it helps us to understand the strengths and limitations of different methods. And then based on those strengths and limitations, we may decide to use one method or ignore it. So it is important to understand what is going on. And the idea of this chapter is to introduce the curve fitting and exponential smoothing and explain what is behind these approaches. So in this chapter, we look at the methods that simply use the historical data to identify and project patterns into the future. That's what we call forecasting. So these methods are called time series methods. They don't take into account any external factors. They just use the historical data of the variable you want to forecast. So if you want to forecast the amount of sales for the next month, if you use time series methods, then they use the historical values of the sales in the past. So they use the past values. Well, you could also use other factors like promotions, like weather, but these are external values. So we don't use them in time series methods. I mean, pure time series method, they don't take this into account. So you might say, okay, but if these methods ignore external variables, how reliable are they? But I can tell you, and research shows this as well. Time series methods are very powerful, even if they don't take into account exogenous or external variables, but they could be robust and accurate. Another thing is, so if you use time series method, then you don't use external factor. If you use methods, and we discuss them later in regression, that include external factors, so you need an additional effort because you have to collect data for that forecast, that predictor you have in your model. And then at some point, you have to also provide the forecast for that variable as well. So actually, it makes our life much more difficult if you include the exogenous variables. I don't know if you can see this bullet point at the bottom, but myself, I can't see it, and I don't know how to get rid of this. Okay, so yeah, another advantage of time series method is they can be automatic. So you don't actually need any intervention from users. They can automatically, tune parameters, optimize them, and then generate the forecast. Okay, let's talk about curve fitting. So we will discuss what are the common types of curves, what is a good fit, and then what are the strengths and limitations of curve fitting. Basically, when you talk about forecasting, this is probably the first thing that comes to mind. We have a historical data, let's fit a curve on this, and then use it for forecasting into the future. So the idea of curve fitting is to find a curve that fits the historical data. And then after that, we want to extrapolate that line, to forecast the future, okay? So, for example, in this case, we have data for 42 months, historical data for 42 months, and then I can fit any line to this. And then after that, I can extrapolate that line. So in this case, it will be just continue like this, and this will provide actually the forecast for us in the future. So what are different type of curves? Basically, you can fit. So here in this graph, you see the same data set, but we fitted different type of curves, right? So when you have a historical data, you can basically fit any type of curve you want. So here we have like a linear, here we have the quadratic, we have logarithmic, here we have the exponential, and then actually you can have a curve like this that actually fits every single point, right? So you can actually use any type of curve to fit your historical data. Then, when you fit the curve to the historical data, you may ask yourself, okay, which one you have to choose, because there are many of them. So in this curve, the red line is the fitted, and then the points are actuals. So basically, what we have to do, and what we do in general, is we calculate the vertical distance between this point and the curve. So we do it for every single point. So we calculate this, and we call this a residual or an error. And then following that, we calculate the sum of squared of this vertical distances, or residuals or error. I use the term residual because in general for fitting, we prefer to use residual, and then we use the error for what we call out of sample or the test set. So, but textbooks, we may refer to both residual or error. But here we mean the vertical distance between the points and the line and in each curve. So we calculate the distance, which is the error, and then we square it, and then we add them together. We calculate the sum of square error. This is also called ordinary least square. And then we actually go for a curve that minimizes that sum of square error. So that is the idea behind curve fitting, and then how to go and identify which one I have to choose. So another important thing is, behind each curve we fit, of course, there is an equation, there is a formula. For example, if you have a linear curve like what we saw in the graph, then we may have something like this. So there is a parameter called alpha, and then beta 0 times time. And then time here is the number of, is the period number. So we start from 1, which is period 1, and then 2, 3, 4, 5, and then we go on, we continue, and the time corresponds to this period number. We can have a quadratic curve. The equation would be something like this. Again, you can estimate these parameters, alpha and beta, and here alpha and beta 0 and beta 1, using least square method. Another example here is exponential curve, right? So there is an equation behind each curve we are fitting, and then we need to estimate the parameters of that curve as well. That is normally done with least square. Now, how well the curve fits the historical data? We said we go for the one that minimizes sum of square error, but there are some measures that will help us to make a decision. In chapter 3, you have seen accuracy error measures or accuracy measures like root mean square or mean absolute error, mean absolute percentage error. So you can still use these measures to judge which curve fitting you prefer. Another measure that is generally used for this purpose is called R squared. And well, there must be a space here, but this R square, if I want to interpret it, is actually something like explained the variation divided by total variation. So it will tell us what fraction of the variation in the actual series can be explained by the fitted curve. And this is something between 0 and 100. And of course, if it is close to 100, it means most of the variation in the data could be explained by the curve. And if it's close to 0, that means the variation in data is not explained by the model or by the curve in this case, right? So this is one way to judge, in addition to the accuracy measure or error measures you saw in chapter 3. But there is a problem with R squared. And the problem is if we use more complex curve, and then by complex here, I mean we just add parameters. You know, in linear, we had one parameter. We had two parameters, alpha, which is the intercept, and then we have a slope, beta 0. And then if I keep adding parameters to this, I can increase my R squared, right? So curves with more parameters tend to have higher R squared. And this is sometimes could be misleading. So if you just rely on R squared, it could be misleading if we just use it. So what we have to do, yeah, just before actually that, this is something that we know in forecasting, and we call it overfitting, right? So if you remember, when we talk about forecasting, in forecasting, what we are interested in, we are interested in capturing the systematic pattern in the data and then project this into the future, right? So we're not interested in capturing the noise, because noise is just random. You cannot really do it. And if you do it, it will be a mistake. You will see huge errors in the future. But if you try just by adding more parameters to your model, if you try to 100% fit your historical data, then actually you're trying to follow noise as well, right? So if you fail to capture the systematic pattern in data, this is bad. And if you try to follow the noise and overfit, this is bad as well, right? So, and this is known as overfitting in the area of forecasting and modeling in general. So to avoid this, we can actually use something called adjusted R squared. And this adjusted R squared give a penalty with curves that has more models, more parameters, okay? So if you remember in chapter 3, you also discussed something called information criteria that has a similar concept. So in information criteria, we try also to have a balance between having a good fit and with a reasonable number of parameters. So to decide which curve we have to use, you can, of course, look at the R-square, but you need to be careful because you know that the R-square could be misleading. So instead, it's good to also look at the adjusted R-square and information criteria. These are more reliable criteria, adjusted R-square information criteria, because they give the penalty to the number of parameters in your curve. For example, with the data I had in the previous example, I just fit a curve, a linear curve to this, and then I can calculate the R-square and adjusted R-square. Well, and in this case, it tells me, so around 60% of the variation in the data cannot be explained by this fitted curve. And probably we understand why, because there is a seasonality there, and this is just capturing the trend, while the data has both trend and seasonality. So only 60%, only 40% of the variation in the data could be explained by this fitted curve. So while, you know, fitting a curve seems to be simple to implement it, and actually it is simple to implement it, but in forecasting, we are not really interested in fitting. Instead, what we are really interested in is getting an accurate forecast, right? That's the most important thing in forecasting we need to remind ourselves. Okay, a good fit is desirable, but there is no guarantee that it gives us an accurate forecast, right? And then there is actually a nice, really well-written article. If you're interested, you can read this, that explain this very well, to explain or to predict. Are you interested in explaining things, or are you interested in predicting things? And then I said, there is no guarantee that a good fit leads to an accurate forecast. So you need to have this in mind. So if you're relying only on fitting and fitting a curve in your data, and then you use that to forecast, you may see actually surprising results. So you need to be careful with that. And of course, you have maybe discussed it in chapter 3, but you know, in the second book we will read later, we will discuss this in more detail as well. So what would be then the right way to choose between models? Okay, so that was about the curve fitting. So the first thing that comes to mind in time series forecasting is, let's fit a curve, and then after fitting a curve, let's extrapolate it to forecast the future, right? So another alternative is using exponential smoothing. So one problem with fitting curve is you could have a trend that actually goes increasing or decreasing forever. So there is no way to change the rate when it comes to forecasting. So exponential smoothing is one way to overcome these issues. So exponential smoothing will take into account the trend and seasonality and the level of your time series. And they update also the estimate of the trend, but in curve fitting we couldn't update this, right? They update this estimate when they receive a new information about an observation, right? So in exponential smoothing, basically we have level, we have trend and seasonality, and we could have a combination of all this, and then somehow we need to find a way to combine them. And I said with exponential smoothing, the rate of change, the rate could be changed, and the rate of this change is controlled by what we call as smoothing parameters. So there are different types of smoothing parameters: alpha, beta, phi, and gamma. And then by the end of this session, you will learn about this as well. So the first and the simplest type of exponential smoothing method is simple or single exponential smoothing. People call often this as SES. This is a very simple method, but is widely used in practice. And it doesn't take into account any trend and seasonality. So if you have a time series with trend and seasonality, well, SES couldn't be very helpful there. But if you have an actual time series that has a level, and then there are random variations around that level, then SES could be actually an appropriate approach. So if the time series will vary randomly around a level, the task of SES is to estimate what that level is, right? So this is two time series I just generated randomly. So here you have what I call the level, is just 100. And then here you have what I call noise or random series. Okay, this is generated with normal distribution. It's completely random, right? So if you have something like this, and if I put them together, then you see the blue line, right? So the blue line is basically a constant plus those random variations. So each point here is the constant, the red line plus the random variation. You get this point. At this period, you have the red line plus random variation, you get this, okay? So if you have something like this, then SES task is to estimate basically this level. So the idea of SES is to get the best estimation for this red line. So we cannot follow those random variations around this. We go for the best estimation of the level. So this is what we call level in exponential smoothing. Is the first component of an exponential smoothing method. And this is the data I generated basically. So there is a date, as you can see, there is a level and there is a noise, and then I add level to noise and I get this series. So this plus this will give me this series. So, and it is clear from this that when I talk about the level, what I mean by a level. So now the question is how SES updates the estimate of the level. There is an equation for SES, and the equation is the forecast for next period is equal to the current forecast plus alpha times forecast error, and then I can replace this forecast error with latest observation minus current forecast, right? And I can rewrite it in this form. So in textbooks, you may find different representations or formulas for SES. So you can use any of this, but so I refer to SES with this last equation here. So forecast for next period is equal to alpha times latest observation plus 1 minus alpha times current forecast. So if I want to forecast for next period, then I need to decide what is the value of alpha I'm using first of all, right? And then I have, of course, the last observation, the observation from the previous period, and then the forecast as well, right? So this is not right, but so here I have to I have to correct it, but here it says the alpha, the value of alpha is between 0 and 1, right? So alpha can change between 0 and 1. So if is equal to 0, it means the level never updates. So it's just a constant mean. But if alpha is equal to 1, the level updates completely. So you may know this is called a naive method. So now what does a big or small value of alpha means? So if we have a higher value of alpha close to 1, it means we give more weight to the latest observation. So it means more recent observations are important for us, right? That's the interpretation we have for the alpha. And alpha controls the flexibility of the level. So when you fit a curve using SES, depending on the value of alpha, you may have a very smooth line close to constant, or you may have a very fluctuating line when alpha is very high. So you can see it actually in this example. So I changed the value of alpha from something very close to 0 to something very close to 1. So you see that when alpha is lower, we have like a smooth, a constant line, and it is less reactive to changes. But as alpha increases, it becomes more reactive to changes. And then you see it here, it is like a naive. So the fitted value for each point actually is the value from the previous period, almost. So this is how changing alpha will impact the curve we fit to our historical data. So there is, I think there must be, sorry, I have to, I think I have to go here because there is some issue, I think. Can you still see my screen or?
No, we cannot see at the moment.
Okay, let me move to. Can you see this now?
Yes, we can see now.
Okay, because I think there was some problems with my PDF file.
Is it HTML?
Yeah. So this was HTML, and I converted it to a PDF. Then I think there was some issues, but yeah. So so this is how changing alpha will change the smooth lines. And then, well, why we call it an exponential smoothing? Because you know, for any alpha values you have, the weight changes exponentially. So you can try it yourself. Here I have tried with an alpha of equal to 0.5, and then as it goes from period 1 to the older periods, I mean to the latest period to the oldest period, the weight changes exponentially. So that's the reason basically why we call this exponential smoothing, because the weights of observations in the past changes exponentially. So now let's look at this very simple example. So in this example, you have the period, so it is week 1, week 2 to week 10, and then here you have the actual sales up to period 7, and you want to forecast for period 8, period 9, and period 10. So how you do it with simple exponential smoothing? Well, I have to forecast the first period, right? I'm here. So if I follow the equation, so I have to say forecast for this period is equal to alpha, and then here we just use an alpha equal to 0.2. So you can change it to any alpha if you want. So to forecast this period, I have to say, so forecasting this period according to the equation is alpha times the previous actual demand, right, minus the forecast I had for that period. But the problem is we don't have any period before this, right? This is our first period. So what I have to do, well, I have to just provide the first forecast myself, and we call this an initial value. So I have to initiate the process by providing a value. And this could be, of course, optimized as well. But you can, just to see how it works, you can work with any number. Actually, it could be even just the value you have here. So my first forecast is just equal to the value I see here, right? So I need an initial value to start my process. But then to calculate this, it is easy. Now my second period, so is equal to alpha times the previous observation I have plus 1 minus alpha times the previous forecast I have. And then I get 49 for this period. And then of course I can, this is a recursive process. I can go on and then continue doing this up to here, right? So here, the forecast for this period is alpha times 60 plus 1 minus alpha times 50, and I get 52, right? Now, as you can see, I have 3 periods to forecast, 8, 9, and 10. But I just repeated the same value from here to here to here. Why? Because this is simple exponential smoothing. It doesn't take into account any trend or seasonality. So if you forecast multiple steps ahead, more than 1 period, then you have to just repeat the latest forecast you generate. Okay, I think that is something you need to remember. This is how simple exponential smoothing works. So basically we have 2 parameters in simple exponential smoothing. One is alpha, and then one is initial value. And then we can optimize these parameters using sum of squared error or mean squared error. So here you have the actuals, you have the forecast, you can calculate the error, and then you can calculate mean squared error, and then see what are the value of alpha that minimize this, and what are the value of initial values that minimize this. Okay? All right. So that was single exponential smoothing. And single exponential smoothing doesn't take into account trend and seasonality. Now we look at the Holt's method that actually takes into account trend. So in addition to the level we had in single exponential smoothing, now we have trend as well. So if there is a trend in a series, so single exponential smoothing will always forecast too low or too high, depending on the trend, if it's upward or it's downward, right? So we need a method that cope with this, so it allows us to change the trend, to detect the changes, and as we move the time, from period 1 we go to the future, and then later on to the actual future. So by future here I mean period 1, period 2. This is my, in each step I have a future in front of me, and then by actual future I mean after the last historical observation I have, then I don't have any other data, then that's actually the future I have to forecast for, right? So the idea of Holt method is to introduce a linear trend to be included with exponential smoothing method, and the name of the method is Holt. So how it works? I mean, the most important thing about exponential smoothing is if you learn how single exponential smoothing works, then you can actually do it for the rest easily, because the principles are exactly the same. We update level, we update trend, we update seasonality as we receive the latest observation. That's the idea or principle behind exponential smoothing, right? So with holds, it updates two things. It estimates of the underlying level at the current time, and it's estimate of the current level. By current level, I mean the expected change in the level between now and the next period. So if there is any change, that is trend. If there is no change at all, then it is just a level. So we need to update now two things, the level and then the trend. So here now I have one additional parameter called beta. And then beta can change between 0 and 1. And if beta is equal to 1, then the trend is linear. And if it's equal to 0, the trend is linear. And if it's equal to 1, then the trend updates in every single observation as I move forward. Well, I have one more additional initial value as well, because you saw when we did the SES, I need to start my process. And then I had the initial value for the forecast, but now I need also, for the level, I need an initial value for the trend as well. So basically I have two more parameters comparing to SES. So how hold produce a forecast? So updates is estimate of the underlying level of the observation at the current period using this formula. So the current estimate of level is equal to alpha times latest observation plus 1 minus alpha times, now I have to add something related to the trend. So I have the previous estimate of the level plus the previous estimate of the trend. So that's the difference between this equation and the equation with SES. But now I have one additional equation comparing to SES, because I have to calculate the estimate of the trend. So the next step, we update the estimate of the trend using this formula. So current estimate of trend is equal to beta times latest observation of trend plus 1 minus beta times the previous estimate of the trend. And finally, the forecast for the next period is current estimate of the level, this plus the current estimate of the trend, this, and that will give me my forecast equation. Now, with the hold method, if I just use a linear trend, so it may go increasing or decreasing forever, right? But in some cases, like in sales, for example, you don't expect the sales of a product to be increasing forever because it has a life cycle. So at some point it's saturated, right? So how we can deal with this? We can deal with this using damped hold method. And the idea of damped hold method is to say, okay, if I have a trend that increases, at some point, I saturate it. It becomes more like stable or horizontal. So to be able to do this, we need to introduce a new parameter called phi. So here you see the historical data for an example, and then hold method, and then two different phi parameters. So that's what I said. So you know, you see that this becomes more like saturated. It's not just increasing like the first one, which is hold. Here it becomes like this, and then finally it becomes more like a horizontal line. So that's the idea behind the damped hold. And okay, now with the damped hold, we have one more parameter. So there is an additional parameter to the hold method, and the parameter is phi. We can also have the hold with an exponential trend. So if you have a linear trend, so a linear trend might involve underlying observation increase by 3 units per period. So in each period, we add 3, 3, 3. So our observation might be 100 and then 103, 106, etc. So it increases by 3 units. When the trend is exponential, the successive observation might be, for example, 10% more. So the previous, so the successive values or levels might be, okay, 100, then 100 times 1.1, that becomes 110, then 110 times 1.1, 121, etc., etc. Okay, so if you have the exponential, then the way we update the trend, then it is different. So our forecast in this case would be the current level estimate times current growth rate estimate power of H, and H here is the forecast horizon. So how many periods in advance you want to forecast. Okay, so we had hold, we had cess, we had hold, damped hold, and then we have now hold winter that takes care of both trend and seasonality. So in addition to level, we have both trend and seasonality. So when there is a seasonal pattern in this series, this can also change as time goes on, as this was example with the trend. So of course, you know many examples of the seasonality. Well, an example could be a food or drink product may become fashionable at Christmas. So the demand or sales of that particular drink or food will change maybe every Christmas. So hold winter method is the extension of hold. So this should be hold winter. It's an extension of hold. So in addition to the updating its estimate of the underlying level and the trend, it also updates the estimate of seasonal pattern. So I have one additional parameter here that controls the rate of changes, which is gamma, but I have also initial seasonal indices for the seasonality. So it depends on the seasonality. If you have monthly, then you have 12 seasonal indices that says how seasonality changes for each particular month of the year. If you have quarterly data, then you have 4 seasonal indices then says how seasonality changes for each quarter of the year. We call them seasonal indices. Then I need also to have an initial estimation for those parameters as well. So in addition to alpha, beta, and initial values for trend and level, now I have gamma and then an initial seasonal indices as well. So now there are 2 types of seasonality, and then hold winter would be different as well. So we have a additive hold winter, and then we have the multiplicative hold winter. And then the difference is if you have a multiplicative seasonality, then the level or the length of this seasonality will change as the level changes. So as you can see here, this distance is more or less the same. It doesn't matter if I look at it here or if I look at it here. But here, if I look at it here, this distance is actually narrow, but if I go here, it becomes much wider. So if this is the case, then I need to use additive hold winter in the case like that, and I need to use multiplicative hold winter in the case like this. So for the additive case, I have my latest level estimate, latest trend estimate. This is similar to what we had in the CES and hold. But now I have also the seasonal index. So again, the season could be month, day, week, or quarter, etc. So if it's additive, I just use the plus, I add this, and if it's the multiplicative, then I multiply this by the level and the trend. Well, just to have a summary of the exponential smoothing models, there is a classification by Pagel, so you can look at this. So here there is a level and trend, and then here you have seasonality. So if there is no trend and no seasonality, and then you have only the level, that's what you get. And then if you have a linear trend, no seasonality, exponential trend, a damped trend, and then if you have the additive seasonality or multiplicative seasonality, which with each of these, no trend, linear trend, exponential trend, and damped trend. Well, there are more classes as well. This gives us like an idea of different type of exponential smoothing methods. So in the last part of the book, we have a part dedicated to intermittent demand forecasting. Well, we have in time series forecasting, these are a special type of time series where you have zero values in time series. So as you can see here, for example, there is 0, 0, 0, and suddenly there is a non-zero value, 0, 0, and then suddenly there is a non-zero, okay? So if you have a time series like this, then you need a special type of models or methods dedicated to intermittent demand. So if you just use exponential smoothing, it might not work. Well, in practice, people still use CES for this kind of time series, but you need to be careful. You need time series that can take care of intermittent demand. So there is a classical approach called Croston for intermittent demand. This is based on single exponential smoothing. So in Croston, we need actually to calculate two equations. One equation for the size, as you can see here, size, size, size. For the size of your observation or sales or demand. So you need to estimate that. And another thing, you need to estimate the intervals between non-zero demands. Okay, you have zeros and then non-zeros. So you need to have an estimation between the intervals as well. And then finally, you combine these two estimation and you get the forecast for intermittent demand. There are actually many more advanced methods that deal with intermittent demand forecasting. So we may have actually sessions in the future that we look at the intermittent demand in particular, but just to have the idea of what is intermittent demand and then what is the Croston, I think it would be enough for this session. Yeah, I think that was what I wanted to share about this chapter. So if there is any particular question, I'm happy to answer.
Hello, hello.
Hi.
Hi, I just want to understand better. How do you optimize your smoothing parameters, alpha, beta, gamma, and the initial level, trend, and seasonality?
Yeah.
You mentioned that this can be selected by mean square error, but for mean square error, you need some period of data.
Yeah, exactly. So if you, there are many ways to select those parameters. So you can have, if I understood the question correctly, so you can maybe split your data into training and test, and then you optimize the value of alpha and your training. It could be using, again, mean square error, but it could be using AIC or BIC, which is related to information criteria. So you need a period of training to optimize those parameters. But then, if, for example, you perform, let's say, a time series cross validation, then there is no guarantee that as you increase the size of your training, you get the same value of alpha. But anyway, you get the optimal value of alpha for that training size.
Yeah, thank you.
Any other question or anything else you want to say? Just check. Okay, so, well, if there is no question, then we can, I can stop sharing. And then